All right. Due to some technical difficulties on Friday, only half of the um, lecture recorded. So I am going to finish up the other half. So we talked about ways of finding the exact sum of an infinite series um, using, if it's a geometric series, pretty easy. We have a formula for that. If it is a telescoping series of the form 1 over n times n plus 1, we can find that sum as well. What we're going to do for other series is rather than finding the exact sum, we're going to just look for ways to tell whether or not there is a sum, whether or not that series can, the sum of that series goes to a specific value or not. So one way is through the integral test. So if f is a continuous positive decreasing function on the interval from 1 to infinity, and we're going to let a sub n, the nth term in our series, be thought of as the function f at each integer value. Then the series is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. So if you remember back to chapter 6, I believe it was, when we talked about improper integrals, that's where we're going to kind of continue. So that's basically what this is saying, is if the integral from 1 to infinity of that function is convergent, then the sum is convergent. And if the integral from 1 to infinity of that function is divergent, then the sum is also divergent. So the sum follows what the integral is doing. We use 1 to infinity, but really it does not have to start at 1. It could start at, as long as the function is defined, it could start anywhere, as long as it's defined on that interval. Also, the function does not have to be decreasing all the time. Basically, we just want it decreasing for large values of x, and we'll take a look at how to tell that here in just a moment. So determine whether the series ln of x divided by x converges or diverges. So this one, we would go from 1 to infinity. Look at the integral. Now, technically, the sum, I probably should have said ln of n divided by n. But in this case, this is a substitution problem. And it's that one time in 1,000 where using substitution and our u is not the denominator. I'm going to leave the limits as 1 to infinity. So I get u, and the 1 over x dx gets replaced by du. So this would equal 1/2 u squared. But u is the ln of x. So this would be 1/2 ln of infinity squared minus 1/2 ln of 1 squared. And as ln, as we go to infinity, that goes to infinity. So this would be divergent. Another test that we can use is the p-series test. And this needs to be changed. This should be n to the power of p. And it's the same as the comparison, the parameters are the same as the comparison test we talked about with improper integrals. If p is greater than or equal greater than 1, then the series is convergent. If p is less than or equal to 1, it is divergent. Excuse me. So we're going to use that for comparison, the comparison test. Testing by comparison. So suppose we have two series AN and BN with positive terms. And then suppose that B of n is convergent and A sub n is always less than or equal to B sub n. So if the larger series B sub n is convergent, then the smaller series is also convergent. If B sub n is divergent and A sub n is greater than B sub n, then the larger series is also divergent. So whenever we use, or usually when we use the comparison test, we want to compare the given series with a p-series. So determine whether the following series converges or diverges. We have the series n goes from 1 to infinity of 5 over 2n squared plus 4n plus 3. This series is pretty similar to 1 over n squared, which is a p series where n is, where p is greater than 1. So it is, so 1 over n squared would be convergent. And so we want to compare this. So we're going to look at, how does n squared compare to 2n squared plus 4n plus 3? Well, because n has to be 1 or larger, we're going to get greater than there. Okay. Now, if I take the reciprocal, that switches my inequality. The last thing I want to do, I'm going to multiply both sides by 5. because 1 over n squared is convergent. Five over n squared is also convergent. So if we have a convergent series and we just multiply by a constant, that resulting series is also convergent. Then I can say by the comparison test, I should do this. Series n goes from 1 to infinity. 5 over 2n squared plus 4n plus 3 is convergent. We'll also talk quickly about the limit comparison test. Suppose that a sub n and b sub n are series with positive terms. And if we have the limit as n approaches infinity of a sub n divided by b sub n equals c, where c is a finite number and c is greater than 0. So it's going to equal a value. Value has to be greater than 0. Then either both series converge or both series diverge. And again, it's going to help to know, one of our two series, whether it's convergent or divergent. So again, it's a comparison test, but this time looking at limits. So again, using those p series will be very helpful. Here we have the series n goes from 1 to infinity of 1 over the quantity 2n minus 1. So 1 over 2 to the n minus 1 is very similar to 1 over 2 to the n. 1 over 2 to the n is a geometric series with r being 1/2 and a being 1/2. So this is a convergent series, the 1 over 2 to the n. I am going to compare it with 1 over 2 to the n minus 1 with the limit comparison test. And what I'm going to do, excuse me, is I'm going to put my 2 to the n first in the numerator and 2 to the power of n minus 1 in the denominator. So the reason being, I want to get this part moved back into the numerator because it will be easier to deal with that subtraction if it's in the numerator rather than in the denominator. So this is division, and division is the same thing as multiplying by the reciprocal. So I would have 2 to the n minus 1 over 2 to the n, which would be the limit as n approaches infinity of 2 to the n over 2 to the n minus 1 over 2 to the n. Well, I have something divided by itself, that's 1. As n goes to infinity, 1 over 2 to the n goes to 0. So that gives me a 1, which is a constant that is greater than 0. So by the limit comparison test, the series n goes from 1 to infinity of 1 over 2 to the n minus 1 is convergent. And there is your assignment. Sorry that this took a little bit of time to get posted. If you have questions, feel free to ask during class this coming week, or send me an email or a message on Schoology. Have a great day, and we'll see you later.